Hello friends, welcome to Electronic Circuit Hub. So today we are going to understand about design and simulation of dual output DC-DC converter. Okay. So if I say the dual output, that means this DC-DC converter is going to generate both positive and negative outputs. So that is why it is dual output DC-DC converter. And if you look at the output voltage here, I have mentioned is it is going to generate 12 volt and positive 12 volt, and it is also going to generate negative 20 volt with the input of 3.5 volt. Okay, with the input of 3.5 volt, by using this DC-DC converter IC LT1945, you are going to generate both positive and negative output, that is 12 volt and 20 volt. Okay, if you go and look at the data sheet of LT1945, so if you look at here LT1945, how what you can say here is this is dual micro power DC-DC converter with positive and negative outputs. Okay, let's first look at the data sheet of LT1945, and then later we are going to understand the design of dual output DC-DC converter, and I'll run the simulation and I'm gonna show you the waveforms there. Okay, so if you look at now the features of this generates a well regulated positive and negative outputs with low quotient current is 20 microampere, which is very low in active mode, and less than 1 microampere is greater than 1 microampere in the shutdown mode. So what you see from here is it operates with input voltage of very low, V in as 1.2. Okay, so V, if you have the input voltage which is very low and close to 1.2 volt, it is going to generate the output, it is going to boost up the output with low V sat and 250 millivolt at 300 milliampere. Okay, and it can generate the maximum high output up to plus minus 34 volt, so it can generate plus minus 34 volt outputs. And if you look at the application, if we use this in case of small TFT LCD panels, handheld computers, and battery backup product and digital cameras. If you go and look at the typical application of this circuit, uh, typical application by using LT1945, how it looks like is here they want to generate the dual output. 12 voltage is the positive output and minus 20 volt the negative output. And if you look at the current versus efficiency, input voltage they are feeding here is 2.7 to 5 volt. Okay, efficiency, if you look at the 12 volt, they are at 10 milliampere, they are achieving around 80% of efficiency, while for minus 20 volt at 10 milliampere they are achieving around 75%. So I would say efficiency is not up to that mark, but somehow this is generating the dual output with the positive and the negative. Okay, if you go and look at the down, this is the pin configuration, you can read it, the pin configuration, you can read these parameters. And let's look at the application circuit. This is the typical internal block diagram, and now they are using this circuit, choosing an inductor. So inductor selection guide for boost converter, and they are also using this circuit as a SAPIC converter. So that's why they have given here the inductor selector guide for SAPIC converter. Okay, you can read out this, I'm not gonna read. So what I do now is in inductor selection for inverting regulator, inductor selection for inverting charge pump regulator, all the things they have mentioned here is I'm going to go again. Then they have given the also application circuit for 32 volt output. Okay, 5 milliampere 32 volt output positive and 32 volt output negative, but I want to generate the output of minus 20 volt and plus 12 volt, the first circuitry. Now let us look at the quickly look at the circuit, and then I'll run the simulation. Okay, so if you look at here, this is V in, and then this V in directly connected to the inductor. This side also, this V in goes to the inductor. Then in this side we have the capacitor connected in series. Then this diode and reverse diode, and this is the output feedback monitor circuit. That's why they have written here NFB1, negative feedback monitor circuit. What about the positive side? We have inductor, we have diode. It's a kind of the boost converter. We have inductor and we have diode, and it has the feedback now, feedback which is connected to FV2, and the output is 12 volt. Okay, so let's, without any delay, let us quickly run the simulation and let us see whether this circuit is generating the expected output or not, how it works. So I run the simulation, and let's say if I zoom this, so first let's look at the output voltage, input voltage. Okay, what is your input voltage? Input voltage is around 3.5 volt. Now let's look at the output voltage. This is my 12 volt output voltage. Okay, now you see we have the ripple at output voltage, but it is 12 volt, exactly 12 volt. What about the negative output voltage? So in case of the negative output voltage, you also see the ripple, but your V out 1 is around, if I click here, is around 20 volt. So what you can see, that this circuit is perfectly generating the positive 12 volt output and negative 12 volt output, okay, with the help of inductor, output capacitor, and the feedback components, diode and feedback components. Okay, so if you look at now the outputs, we are very clear, we are getting the output, the current is low. So 1 get divided by 12, it is, you are going to get the current around 12 milliampere. And the same here for negative current. Let's say how much is the negative current, and negative current I am getting here is around minus 9 milliampere, and the positive current is minus 12 milliampere, right? Minus 12 milliampere. So if I have to show you now the waveform of inductor, so let me delete this current waveform. I deleted the current waveform. Let's look at the inductor waveform for both positive and negative output. So this is L1 waveform, the current flowing through L1, and I want to also show to you the current flowing through L2. So this is L2. Let's look at how it looks like, both L1 and L2 waveform. This will take some time to run the computation, to run the simulation. As you can see here, if you use any kind of inductor in the circuit and in the components, it will take some time to complete the simulation. But what I'm going to do here is I'm going to halt the simulation. Let me halt the simulation, and let's see the inductor waveform. I just uh, halt the simulation, and let's look at the inductor waveform, how it looks like. Okay, so it's still running. The inductor waveform is still running. Keep on running. I'll zoom it and let's look at. So this perfectly fine now. This is perfectly fine, and that is how you'll see the inductor waveform, how it looks like. Okay. So for the positive, you will see this is my 0 volt. I see this is working almost. It's not working in DCM, but it is working in BCM boundary condition. So I have both waveform, that starting from the positive 0 to the peak value of 356 around, and here what I see here is this is my around 0 volt, 0 milliampere, and I am seeing here the the current, positive peak current. And in this case, if you look at here, it's coming even below the 0 for negative 49, and we have peak to peak current for the negative, and we have peak current for positive inductor current. What else I can show you? Okay, so what about the feedback voltage? Let's look at the feedback one. This is your feedback one, and let's look at the feedback two. This is the feedback two, and if I zoom both feedback one and feedback two, it is still not working. It is taking some time. I'm gonna delete now the inductor value. I deleted the inductor value. This is your feedback 1 and this is your feedback 2 voltage. Here I see the feedback 1 is 1.22, feedback 2 is again the same 1.22. Now what we can do here is let's play with the values. Okay, I don't know what value I should put, but let's rather than using 115k, let's say if I using this 130k. Okay, let's say what is going to happen. I'm using this 130k, so I have to run the simulation again. I ran the simulation and let's look at the output now. Okay, only one output. This I can delete V out to. So earlier it was 12 volt and let's see how much voltage I'm getting. Okay. So I'm getting 10.84 volt. What do you mean by this? If I increase the resistance value, I'm getting the lower output voltage. And let's say I'm using here 90k. Let's see what is going to happen. If I use the 90k, just save it, run the simulation once again. And let's see what is the output voltage, how it looks like with the 90k. Okay. So with the 90k, what is my output voltage? I see the stable output voltage now. It's more quite stable here, and I see here 15 volt. Okay, with the 90k, I'm getting 15 volt. What if I change this value? What if I change this value to 47k? Okay, the divider value to 47k. I'm changing this divider value to 47k. I will save this and I will run the simulation again. So now I am, what is the value here? V out I'm getting, and what is the current? Let's look at. Okay. So the voltage earlier with 90k was 15 and still ramping here. Current is 14. Current is very less. Let's look at the voltage. And the voltage, what I'm getting here, stable voltage more or less, and it is around this time 20 volt. With the 47k I'm getting 20 volt here. What about if I change this register as well? Okay, rather than using 24.9, let's use 4.7k. Okay, so thank you guys, hope you understand this simulation. If you have any further question on it, feel free to ask me in comment section.